So in this series of videos, I want to start off with summations and products. Because in programming, you may have already be familiar with that. In programming, we like to do for loops quite a bit. So a for loop, right? And in a lot of cases, or in some cases, we try to avoid them where at all possible. But for a lot of cases, they're necessary and very useful. And so one of the things about for loops, like if I write a for loop like this for I in range, I code in Python a lot, so I'm used to Python, 1 to n, I am going to do some work. I'm actually going to do, just by the sake of like how this algorithm works, I'm going to do I steps of work. And so I'm just going to say I steps, right? Or I ops. And so you're wondering, like, okay, like how do I visualize this? Why is it that if I is equal to 1, I'm doing 1 step? If I is equal to 2, I'm doing 2 steps. And you know, in a general sense, you can imagine that this for loop is iterating over a set of items, and for each item, it's probably adding it to some data structure, like maybe a list, or maybe it's adding it to a map. This is how I represent maps, and it's storing every item in this map or in this list. And then so once it stores, let's just say it stores the first item in this structure. Let's say it's a list, so it'll store like some item here, item number 1. Then when it goes to the next iteration and it stores item number 2, right, it has to do some work where it has to do some changing of 1. It has to modify it in some way. And then when it adds 3, it has to go back and do some modifications to 1 and modifications to 2. And maybe it's doing it just to maintain some sort of like memory or about past items or some sort of ordering. I don't know. But you can imagine this being something that has to be done. And so now to get into the summations part is that we would like to, if we had an algorithm that did something like this, we would like to be able to analyze the number of operations that it would do over n iterations. And I can actually represent the total number of ops that it would do, or operations, with this little summation right here. The sum from I equals 1 to n of I. This right here is the summation operator. And what this means is that you're going to say I is going to start at 1, and then when it starts at 1, we're going to do 1, and then it's going to move to 2, and then we're going to add to it 2, and it's going to move to 3, and then we're going to add to it 3, and then so on and so forth until we get to n. And so it's just summing up the first n numbers. And so for and that's that right here, this whole little sequence right here is when you sum it up, it's going to give you the total number of operations that your for loop is doing over here. If we're assuming that every single step is doing just 1 unit of work, and or every single step that you do, like say like you do right here, you do I steps, like let's say you do 2 steps, then each one is just 1 unit of work to make sure that it sums up to 2. And so the nice thing about summations is that you can manipulate them, or you can reduce them down into like very workable formulas, or the regular formulas, so you don't have to look at the symbol anymore. And so one of the cool things about this summation right here is that we're actually we can actually write this like this. Instead of just running this summation all the way out to n, we can just plug in into this formula right here, and it'll give you the same thing as if you had just sequentially added up all the numbers. And that's very nice. That means that this formula right here represents the total number of operations that this program does up here. And so for a concrete example, let's move down, let's get into a concrete example. Let's imagine that n is equal to 5. And so that's going to be the sum. I can do a better sum than that. The sum from I equals 1 to 5 of I. Well, that's going to be 1 plus 2 plus 3 plus 4 plus 5. And that's going to be 3, 6, 4, 10, 15. It's going to be 15. And to see how this formula works, I can plug n equals 5 into this formula, which is going to be 5 plus 1 over 2. And this is 6, and so 5 times 6 is 30, divided by 2 is 15. And so that's an easy way for you to see that how that matches up. That's not a clear proof, but at least you can get your hands on something tangible to make sense of it. And this is powerful. Why is this powerful? If you think about it, if you're writing a program to do some job and your program follows this general structure right here, then you're going to want to know, especially if you're dealing with large inputs, like here we have 3 numbers, or we have 5 or 3 items here, and we have 5 items here. But what if n was equal to 100? Or what if n was equal to 1,000, or even more? What if n was equal to 10,000, and so on? You would want to know, how many operations your program would have to do for each of these numbers. And you can just, because you have this formula, because you're able to manipulate this summation, you can just sort of take your 100 and plug it in and give you an answer. And this whole formula, and how you can look at it is like, okay, like how does my program work as I expand out more, as I go into larger inputs? If you can then graph this starting at n equal to 1 all the way to n is equal to 10,000 in our case, and see that it looks like kind of like this, right? So it starts to sort of quadratically grow in a sort of way. Maybe not a sharp quadratic growth, but it still grows quadratically. And that's going to tell you that my program it's going to be okay as long as n is equal to 100. This area we're doing fine. My computer can handle it. And then once it gets up to, like, I don't know, this point, or let's not even talk about this point, then we're going to start to run into some problems with our computational resources. And then you might think, wow, what if I had an algorithm that kind of grew like this? Then maybe I could handle 10,000. And that is the basis of how we can actually use math, like the summation operator, to analyze the runtime of our total operations of our algorithm, and then think about how it would grow if we had to deal with large inputs. In the world of big data, you have to deal with large inputs all the time. And we started thinking, it's not going to do so well up here. My computer is not going to be able to handle it. So now let's figure out a better program. And that is what all algorithms is pretty much all about. Using math and analyzing algorithms to do better. So let's talk about products real quick. And so the same way we can write a summation like this, we can write a product like this too. So if I wrote this little symbol right here for the product, if I did the product from I equals 1 to n of I, instead of adding up the sequential numbers, it would just be multiplying the sequential numbers, right? All the way to n. And the cool thing about products, if you remember from your pre-calculus class, is that if I have a product here, I'm going to write it again. The log, if I take the log of this product, I'm writing it like this because it could be any base. The log of this product is just equal to the sum of the logs. And so we're able to use our logs to be able to transform this product into a summation, which is, and maybe you don't agree, but I think it's a lot easier to think about summations. And this right here is going to be the same thing as this right here. They're going to give you the exact same inputs, and please work that out, just to prove it to yourself. And right, we're talking about translating products into sums, but there's a nice property of summations, and it's the linearity property. I think linearity is always important when talking about anything. But the linearity property is like this. If I have this sum from I equals 1 to n of some constant times a sub I plus some constant times b sub I, right? Or not, so not some constant, just b sub I, sorry. No constant, this is the only constant here. Then I can rewrite this as c times the sum of I equals 1 to n of a sub I plus the sum from I equals 1 to n of b sub I. And then in order to analyze our algorithm or analyze the summation, I can just analyze these, individually. And that's a whole lot easier than analyzing this entire summation together. And so that's a very interesting property about summations. And that's pretty much all for summations and products. I think it's time now to move on to talking about series and sequences. So in this video, I want to talk about series and sequences. And so we talked about a summation, and we had this summation here. when I equals 1 to n of I, and we said that this is the same thing as just adding up all these numbers all the way up to whatever we define n to be. And we came away with this formula, n times n plus 1, to represent an easy way for us to compute this entire sum without iteratively having to add them up using a program of such. And we used it to actually analyze our operations. And so I want to connect how we even got to this point. How do we get from this summation to this formula? Where does this formula come from? And I want to first note that this is a good time to talk about our first type of series, and it's the arithmetic. Let me write that again, sorry. Arithmetic series. And so there's the difference between a series and a sequence is that a sequence is exactly what it sounds like, a sequence of numbers. The series is the sum of all of these sequence of numbers. And so this is the sequence, and then if we were to add all of these up and get the total, that would be the series. And so how do we get this? This right here is actually, this whole sequence right here is an arithmetic sequence. And so what is an arithmetic sequence? Well, an arithmetic sequence is going to be of this form. We have some starting value a, it's 1 in our case up here, and then the next number is going to be that value, 1 in our case, plus some constant d. And then we're going to have the next value is going to be a, our first number again, plus d plus d again, right? And more often, instead of just doing d plus d, you'll see this written as 2 times d. It's a lot easier it takes up less space. And then again, it'll be a, our first number, plus d plus d plus d, which is just 3d. And that sort of thing will carry on all the way down to our first number plus n minus 1, not n, times d. And why is it n minus 1? Well, it's because we just had a here. D was not added to a. And so this is the first entry, and we're adding nothing. We're adding 0d. This is the second entry, and we're adding 1d. This is the third entry, we're adding 2d. And so fourth is 3. And so like if this was the nth entry, we're going to be adding n minus 1d. This number is always 1 less than the index of the sequence. And so what happens here is that we can write the sum of this sequence. It's commonly written like this, s sub n, and its general formula follows this right here. 2 times the first number plus n minus 1 times the common difference, that's what it's called, and it's all divided by 2. And so if you look at, and let me write this down, so a is going to be the first, it's actually called a term, and then d is going to be our common difference. And so if you look at this first summation here, a is going to be, let's look at this, a is going to be, I'm going to write this down here, I'm not going to stay up here. If you look at that, well actually let's stay up here for just a second. So a is going to be 1. And then if you notice, every single one of these is just going to be 1 plus 1 times d. Or no, 1 plus n minus 1, whatever, or I minus 1 times d. So this first one, this number 2 right here is going to be 1 plus 1 times d, which is 1 plus 1 times 1, sorry. And that's going to be 2. And then this is going to be 3. 3 is going to be 1 plus 2 times 1, which is 3. And this is going to be 1 plus 3 times 1, right? And so in our case, d is equal to 1. And our series follows this our sequence follows this format here. And now, how do we get to n times n plus 1 divided by 2? So how do we get this formula, n times n plus 1? So remember, a is equal to 1, d is equal to 1. Let's use this right here, our general formula, and let's plug everything in. This is going to be n times 2 times 1 plus n minus 1 times 1, all divided by 2. And doing a little bit of algebra on top, you're left with n times 2 plus, and this is just going to be n minus 1, n minus 1. all over 2. And if you notice, we have 2 right here and a negative 1 right here, so that's 2 minus 1. And I'm going to save some real estate. The inside parentheses is going to be n plus 1 divided by 2. And this is the exact same formula we got up here. And so that's how we were able to get this formula. So we realized this is an arithmetic sequence. And then an arithmetic series, the general formula for solving its summation, how much it sums up to, is this format. We realized that a is equal to 1 and d is equal to 1 in our case. And then we just plugged it in and did a little bit of math, very little, and we were able to come away with our formula. And that's how we analyzed the arithmetic series. And so that was an actual general program structure that we identified as an arithmetic sequence, and then we solved the sum of that arithmetic sequence using this formula, and was able to come away with a formula that we could use to analyze the number of operations our program did. And I hope by now that you're sort of understanding how math is deeply integrated into analyzing programs. And so there's a few more that I want to talk about that are still seen, in programming quite a bit. We're going to see the geometric series. Let's first talk about a geometric sequence. A simple one is this one, where we have 1, 2, 4, 8, all the way up to keep going. And so a geometric series is of, this form, right? There is some initial term a, which is 1 in our case, and then there's some common ratio, not common difference, but common ratio of this right here, I minus 1, raised to the I minus 1, where I is just the index that we're at in the sequence. So this would be I is equal to 1 here, I is equal to 2 here, I is equal to 3 here, and I is equal to 4 here. And so in our case, right, we see that every single time in a geometric series, you're multiplying by some common ratio. And our common ratio here just happens to be 2, because this is going to be times 2, this is 2 times 2, this is 4 times 2, and so on and so on. And so we can say that a is 1 and our common ratio is 2. And that makes sense, right? If we look at this first number here, why is this equal to 1? Well, if we plug 1 into I, that's going to be 1 times r, which is 2, raised to the 1 minus 1 is 0. We know that this is 1, and so 1 times 1 is 1. And if we jump forth to the fourth entry right here, number 4, well, that's going to be 1 times 2 is our common ratio, raised to 4 minus 1, which is the third, and 2 to the third is 8, and 8 times 1 is 8, and there we go. And that is our geometric sequence, and we can analyze the sum of a geometric sequence the same we can an arithmetic sequence, just with a different formula, because now we have a common ratio. And so here's how we write this common ratio, or the sum. So the sum of a geometric sequence is going to be of this format, right? We can look at it kind of like this. The sum from I equals 0 to n minus 1 of a r I. Pretty much. That's it right there. It's not pretty much, that is it. And this is equal to this right here. 1 minus r to the n divided by 1 minus r. And how can we see this with a concrete example? And so let's start off with an example where we have, now I'm running out of time, so I want to make this super quick for everybody. A is equal to 5. We start with 5. R is going to be equal to 0.5. And just trying to make things a little bit different. And we're only going to go out to n is equal to 3 to keep this short. And so we're going to use this to write the summation as from I equals 0 to n minus 1 is 2. And so that's going to be 5 times, I'm going to write 1/2 instead of 0.5, to the 0th power, plus 5 times 1/2 to the first power, plus 5 times 1/2 to the second power. And, doing this math out, we can see that this is equal to 5, because this is going to be equal to 1. This is going to be 1/2, and so we're going to be left with 2.5. And then this is going to be 1/4, and so 5 over 4, that's going to be 1.25. And that's going to give us 8.75 for this summation. And if we use our handy-dandy formula right here, a times 1 minus r to the n over 1 minus r, this is what we get. We're going to get So make sure everything matches up. 1 minus, I'm going to keep it with 0.5 to the n, all right, divided by 1 minus 0.5. And this is going to be equal to 5 over, the top part evaluates to 8.875, bottom part evaluates to 0.5, and then this is going to be equal to 8.75. You can check it on your calculator and it matches up. And so that's a geometric sequence. And sometimes you could find yourself analyzing a program that follows a geometric sequence, and you can bound it above, or you can analyze its operations using the summation formula here. And so really quickly, I want to go through another one. Really quickly, we won't go through an example, but I want to talk about the concept of telescoping. Telescoping. Right, and this has came up in proofs before for me. And so for this telescoping, right, I'm going to just call it telescoping. Okay, it just states that for any sequence, it's a powerful statement, for any sequence such that we have A0, A1, all the way up to AN, that the sum of all of the numbers, the sum of the difference between all the consecutive numbers of AI minus 1. All right, so we're going to take, like, this would be like, well, let's just finish this. This is just going to be equal to the last number subtracted off by the first number. And why is that? This on a sequence is going to look like such. It's going to be like for A0, A1, this is just going to be like, okay, A1 minus A0, right? We start off with subtracting these two, and then I is going to go to 2, and then we're going to do, okay, A2 minus A1, right? And then we're going to do A3 minus A2. And the idea behind telescoping, and we're going to keep doing that, is that every number is both added in, and it is also subtracted out. So here we added in A2, and here we subtracted it out. We added in A1 here, and then we subtracted it out. But what got left in? What got left in is this negative A0, and what gets left in is the number that's at the end, right? AN got added in, right? But it never got subtracted out like AN minus 1 did. And so that's the concept of telescoping, is that the sum of the difference between each of these numbers in a sequence is just the last number in the sequence minus the first one in the sequence. And so it's going to be AN minus A0, and that is telescoping. And you'll see it in proofs, and I think that is it's a very interesting property of summations just to think about in general, and I think it's important. So in this video, I want to talk briefly, very briefly, about bounding summations. And so starting with our original example, you remember we had this summation that represented the number of operations for our general program, and we said that this formula right here is going to give us the number of operations that this program would do over any n sequential iterations. And in programming, what we like to do is we like to bound the number of operations that we are going to do, and use that bound as sort of our, how we think about the runtime, or the number of operations that our program is going to do. And so this formula, and why do we do that? It's actually easier. It makes it easier to think about our programs. It makes it easier to analyze them, because asymptotically, as n goes to infinity, we know for a fact that the number of operations that our program will do will never, ever, ever pass this point if we're able to bound it. And that's a very powerful statement, especially if we know that we're going to be dealing with large inputs, but we don't know how big. We don't know how big it could possibly be. And so if we expand this formula out real quick, let's just take the 1/2 out, and then we're left with n times n plus 1. And this is also, leaving the 1/2 out is going to be, and then, just sort of distributing here, is going to be n squared plus n. And this is sort of what our function is going to represent. And this is like not something that I want to have in my head when I'm thinking about my program. It would be much nicer to do this, to say, okay, right here, every iteration from I equals 1 to n, we're going to just be adding up I. But we know that this whole sum right here, we know for certain, and we can all agree that it's not going to be, the sum of I equals 1 to n of I is not going to be as high as this, the sum from I equals 1 to n of n, right? Because that means here the first number that we have is going to be 1. So we're going to do 1. And then the next number is going to be 2. And we're going to be 1 plus 2. Here, we're just going to go straight to adding 10, or n at the start. And so if we had n is equal to 10, or n is equal to 5, let's say n equals 5. If we had n is equal to 5, right, in our first case, number 1, and I'm going to write number 2. Number 1, we're going to have 1 plus 2 plus 3 plus 4 plus 5. In the second case, the sum from I equals 1 to n of n, it's going to be 5 plus 5 plus 5 plus 5 plus 5. And this one right here is for sure going to be bigger. And so we could easily say, without a doubt, that this right here is for any sort of n is going to be bigger than this. And what this means, this sum right here, this is actually just the same thing as n squared, just a quadratic function. And why is it n squared? Well, if you have the number n and you add it up by itself n times, that's going to be n squared. If we have 5, if 5 is n, and we do 5 plus 5 plus 5 5 times, then you're going to get 25, which is 5 squared. And that is why this is n squared. And so we can say that the number of operations of our program, our general program, is for sure, no matter how large n can be, it can be n is equal to a trillion, all the way out to infinity, it will never, ever, ever, the number of operations will never, ever, ever pass n squared. And so how would we look at this? Like, how would we graph this? I want to graph this real quick. I want to graph this formula and then this formula to show what the bound really looks like to drill this point home. And so here I've graphed, I'm using Desmos. Desmos is a really powerful tool for graphing. And so I have graphed n times n plus 1 over 2 right here. This is the red line. And then I've graphed x squared, or n squared in our case. And as you can see, that if for really small inputs, we do actually see n times n plus 1 over 2 actually have more operations than n squared. And I know I said, like, no matter how big the input is, but I'm talking about asymptotics here, where we do reach a certain point at n equals 1, the first iteration, right, and which is all we really care about. N is equal to 1 because we're dealing with 1, 2, 3, 4, 5 in terms of the sequence, where for all of infinity, it doesn't really matter how far out we go, and we really only care about past 0. No matter how far out we go, really large numbers, that n squared is always going to be bigger. It's always going to give you a higher number for the same value of your iteration than our other formula. And we can rest assured that n squared is going to perfectly bound our number of operations that we had calculated for all of infinity, no matter how many iterations we do. And n squared is a lot simpler function to think about than n squared plus n, divided by 2, or n times n plus 1 over 2. So that's why we do that, and that is one way, that's how we can actually bound summations and then graph them. So in this video, I want to talk about sets. So sets come up quite a bit, and they don't come up as much as I think they come up as when we're thinking about different types of algorithms that we're writing, or we're trying to do different operations on data. I believe thinking in terms of sets is a lot more important than just the data structure themselves. But you do a lot of operations on sets. It's actually quite common. And so what is a set? I would define a set as a collection. So it's a collection of distinguishable, let's call it distinct objects. And these objects are called members, or we can actually call them elements. Members or elements. And one important property is that a set is unordered. So if you put the numbers 1, 2, 3, 4, 5 in there, and they come out that way, it just so happened to be happenstance, you know? There's no particular order to any objects in a set. Usually it'll come out like 3, 5, 1, 2, you know? And it does not contain, I want to be clear on the distinct property, it does not contain duplicate elements. And so, for example, this right here, and this is kind of how this is exactly how a set is normally referred to, is with curly braces. So this set is a valid set, but it doesn't have to be ordered, right? This is a valid set as well of these three elements, 2, 1, and 3, the numbers. But this right here, 2, 2, 1, and 3, this is not a valid set because it doesn't satisfy this property of no duplicate elements. And so a bit of notation here, okay, is that if I have some element x and it is a member of a set, then I can write it x and then this symbol right here, x, I say x is a member of S, some set S. And that's what that means. And if, for instance, I have a set that has nothing in it, like, for instance, if I just do that, there's nothing in this set, then I can just write this as the empty set. And so this means the empty set, this x means, this symbol right here means that x is a member of S. And you'll commonly see when people are talking about sets, you know, they'll draw like a circle, you know, and then they'll, you know, put some objects in there, and that's sort of how they're visually represented. But let's step into some concrete operations we can do on sets. So some common operations. Sets are really important, and these operations are really important when you're joining tables. Like if you work in SQL and you have two tables and they have like a list of rows, like a list of data, and each one like a tabular structured data set, and each one has like different sets of data in it, and you want to join it on like some field, or you want to find out like what's in this table but what's not in another table. These things sort of come in handy. And so the first one that's probably the most popular that you'll use a lot of is the intersection. And so the intersection between two sets of objects, it can be denoted by this symbol. So if I have two sets A and B, the intersection of A and B is going to be denoted like this. And this is just any object X such that, that's what that colon means, such that X is a member of A and X is a member of B. And visually represented, you have this set here and this set here. Like it looks like your classic Venn diagram, which it is. And the intersection is everything here. And this becomes very important, you know, viewing things like this whenever you're using SQL and you're trying to join two sets of data. Maybe you have A as a data set of books and B as a data set of authors, right? And you're trying to join these two data sets to figure out like, okay, this one's like, you're trying to figure out you're trying to pull this data set together to see like, okay, I want to figure out what is just, you know, all the books, all the authors that actually have a book, right? Because these are all the books. These are just a list of authors. And some authors have tons of books, some have one, and then some have none. And I want to join them together to see which authors actually have a book. And that's what the intersection would do for you. The union, this is used quite a bit as well. If I have a data set A, and we union it with B, this is going to be equal to, we can write it more formally like this, any X such that X is a member of A, or, it's a lot more inclusive, or X is a member of B. And that's the union. And you can visualize this, how we did the intersection, you can visualize the union like this. You have A you have B. It's just going to be pretty much everything on the outer skirts. Everything that's in this whole entire area. We don't count anything that's in the intersection. We only count it once. We don't want to count it twice because that'd be overcounting. And so the next one, and the last one is the difference. Now the difference is actually very important, and it's kind of tricky. No, it's not kind of tricky, but if you hadn't seen it before, you'd be kind of like, what? So A minus B, I can subtract two sets, and that's going to be the same thing as finding all x, members x, where x is a member of A, but it is not, and, right like this, and x is not a member, like that. That's how you do not a member of B. And so, this is how you would visualize the difference between two sets. So if I have this set A and this set B, I want everything that's in A, but it's not in B. So this intersection cannot be a part of it because it's also part of B. So it's pretty much everything over here. This is the difference. And that's a pretty, these are the three main operations that I can think, that I thought was, useful to tell about. We talked about some notation, and we defined what a set is. Remember, it's unordered and it does not contain duplicates. All right, so in this video, I want to talk about some other properties of sets. De Morgan's laws is going to be the main focus, and then we're going to go into some other properties as well. So De Morgan's laws. De Morgan's laws. So De Morgan's laws, there's two right here. But number one, the first one we're going to talk about is this right here. A minus, if I have three sets, A, B, and C, A minus, or the difference between A and the intersection of B and C, it must be the same as A minus B union with A minus C. And this is the first one. And so just to help everyone sort of think about what is happening here, let's draw three sets, A, B, and C. Okay, A, B, C. And let's start with this one first. So first off, we know that the difference is A minus this right here. So let's first solve this portion. That's going to make things easier. So B intersect C. B intersect C. This is going to be, if we can kind of look through all these rings, it's going to be this portion right here. That's B intersect C. And so this is going to be the set that we want to find. Now we want to find A minus this right here. Okay, so A minus this right here, this is the difference. And so this is everything that is in the set A, but is not in this set right here. Well, the set A, this is the boundary of A if we can look through the rings. And so we know that this right here is in A, this little portion right here, but we want everything that's in A, but is not also in this little set. So that's also in this little set, and so let's not include it. And so what that's going to wind up doing is that we know that this is also not in that little tiny intersecting set, everything over here. So I'm going to draw this a little bit dark. Okay. And we also know that this is a part of A and it's not in there as well. And so everything that I'm shading really dark is going to be what this right here, I'm going to round it out. All of this right here, okay, is this right here. And we're going to leave out this portion in the middle. And so let's go over here and let's apply the same logic to this side. So we're going to draw A again, we're going to draw B again, and then we're going to draw C again. This is A, this is B, this is C. And so the first part, let's focus in on this first part. Let's go left to right. We want to figure out what is everything that's in A, okay, but it's not in B. And so here's the boundary of B, here's the boundary of A. And so everything that's in A, but is not in B, is going to be this right here, right? That kind of cuts off, that hits the boundary of A and B. We're going to label this star. So this is star. And we're going to union it with this over here. So what is A minus C? Like, what is everything that's in A, but it's also not in C? Well, if you think about it, everything that's in A that's also not in C, this right here is our problem. That is not something that is in A, but not in C. So let's, oops, sorry. Let me redraw C. I mean, that kind of helps because we're getting rid of it anyways. So we're going to redraw C. So this right here, this is in A, but it is also in C. This is in A, but it's not in C. This is in A, but it's not in C. And so what we're going to do is we're going to union these two things, right? So this is part of A, not in C. And this is part of A, not in B, right? And so when we union them, it's just going to be the same song and dance that we had over here. Everything right here is this right side. And that is the first De Morgan's law, like kind of explained visually. And so hopefully, now the second half right here, I'm not really sure how clear that was, but hopefully that you got it, you know, and you can sort of fill in any blanks that was left there. Now the second part right here, there's another rule. It says A minus the union of B and C is also equal to the difference between A and B intersect with A and C. And we're not going to visually explain this one right here, but I'm going to leave it to you as an exercise to be able to do that yourself. But these are De Morgan's laws, and these are really important, and they really help you to start thinking about more than just two sets. What if you have 3 sets, 4 sets, n sets? You can start applying these laws to n different sets. You know, these laws generalize to n different sets. So next I want to talk about cardinality. And so real quickly, if I'm talking about the cardinality of a set, I'm talking about all the elements of it. So the cardinality of A is just going to be equal to the number of elements of A. So if A's got 10 numbers or 10 items, it's going to be 10. That's the cardinality, and it's denoted by these double lines around A. The next I want to talk about the Cartesian product between two sets. So the Cartesian product, and so if we have a set A, I'm going to take the Cartesian product between A and B. This is going to be more formally defined as all two tuples of A elements of A and B in that order. They're going to come in that order such that A is a member of, little a is a member of A, and little b is a member of B. And so as an example, just to help you with what that means, like, okay, this two tuple and A and B, let's go through a concrete example. Let's imagine that A was 1 and 2. It's the only items in A. And B had items 1, 2, and 3. I know they're ordered, but it's just happenstance. It does not have to be ordered. Sets are, have no particular order. They're unordered. The Cartesian product between A and B, you can imagine just doing this. Let's go to 1, and let's figure out, okay, what's the first pair I can make? 1, 1. This is in A, and this is in A, and this is in B. Good to go. And then let's go 1 and 2. Let me go ahead and get rid of you right here. And let's go 1 and 2. And let's go 1 and 2. Let's get rid of this. And let's move our pointer. 1 and 3. And then finally what we're going to do is we're going to get rid of this, and we're going to switch our pointer to 2, and we're just going to start all over again. 2, 1. And then we're going to have 2, 2, and then 2, 3. And this right here is the Cartesian product of A and B. And so one interesting property of the Cartesian products is that the cardinality of the set A Cartesian product of B is equal to the cardinality of A multiplied by the cardinality of B. And you can see right here in our example, the cardinality of this set is 2 because there's 2 items. The cardinality of this set is 3 because there's 3 items. And we can go, okay, well, if this is the case, then the cardinality of A cross B, or A Cartesian product of B, should be the multiplication of their 2 cardinalities, which is 2 times 3, which is 6. And we have 1, 2, 3, 4, 5, 6. And so that's a tangible example, not a proof, but nonetheless something you can get your hands on and understand. And so that is the big things about sets. That pretty much ends up with sets. I think that's all we need to know. But you have De Morgan's laws, which are really important. We know what the cardinality of a set is. And we also even went as far as to talk about what is the Cartesian product. And so hopefully you have at least a good general understanding of what a set is and some of the operations you can do on them. So in this video, to start off this section on probability, I want to talk about combinatorics, because combinatorics, having a decent understanding of just the fundamentals is very important for being able to understand probability. And so the first thing I want to talk about is very popular. It's called the rule of product. And I believe it's best explained through an example. You've probably seen this somewhere, but let's imagine you run a store and a customer comes in and they pick out some outfits. You run a clothing store. They pick out 4 shirts, 2 pants, and 3 hats. And for whatever reason, this customer really cares and asks you, hey, how many number of outfits can I make with this? And you know the rule of product. And so you go, well, you have 4 different types of shirts, you have 2 different types of pants, you have 3 different types of hats. So that means you can make 8 times 3, 24 different outfits. And this right here is the rule of product. And how this can be visualized is using a tree, is that if I had, let's see, these 4 branches right here are going to represent the different types of shirts, S1, S2, S3, S4. And I'm just going to draw out this tree partially. It would be too big to draw out completely. But, you know, let's just say they decided to pick shirt 1. Well, that means they have shirt 1 plus 2 different style of pants. And then under P1, you know, let's say they actually don't select P1. Let's say they select the second pant style. And so if they select this pant style, they have 3 different types of hats that they can choose from, right? And let's say they pick the first hat. This whole path right here is just one possible outfit combination out of all 24. Because every single one of these nodes, you know, these P1 nodes have 3 hat combinations after being selected. Every single, you know, shirt has 2 different styles of pants. And so if I was to draw out this tree completely, you'd have this bottom row filled up right here with nothing but leaf nodes of different types of hats. And every single path down to a particular leaf node would represent another outfit. And this tree would have 24 different leaf nodes to represent all the different combinations. And this is how you can use the rule of product to calculate number of combinations. And this tree is how you would actually visualize the number of different possible outcomes or outfits in our scenario. And so you can't talk about combinatorics without talking about these 2 things, permutations and combinations. Let's start with permutations because they are the most well-known, I believe. And a permutation is let's start with an example. I think that's the best way to do pretty much anything. Is let's just imagine I have these sets of numbers. A permutation is an ordering of this, a specific ordering of these sets of numbers. And 1, 2, 3 is its sorted order, and that is actually a permutation. But also 3, 2, 1 is a permutation. 2, 3, 1 is a permutation. 3, 1, 2 is a permutation. And let's see, what's another one we can do? We can do 1, 3, 2. That's another permutation. And I believe we have one more. Yeah, 2, 1, 3. all of these are valid permutations. And you're looking at this and you're probably saying, okay, this is just all the different types of ways that I could shuffle these list of numbers, right? I can keep them the same, that's one. I can do this, and so on. And all of these are different permutations or orderings or shuffles of the original set that we had right here, including the original set. That's also a permutation. And so there's a formula for this. And the formula that we use is, let's imagine that k is equal to the number of items in the set. K factorial is going to be equal to the number of permutations you can do, right? And what is a factorial? If you remember, if in this case, the number of items we have is 3, so k is equal to 3. And so we have 3 factorial permutations that we can do. And just to remember what a factorial is, that's going to be 3 times 2 times 1, right? And this is going to be equal to 6. And if you count here, we have 6 different permutations. And these are all the different permutations we can do, and we can use this formula. And so the one thing that that helps me sort of remember, it's just a helpful thing to keep in mind, is that with permutations, the order of the items does matter. So for instance, 1, 2, 3 right here, this is not the same as 3, 2, 1 because the orders are different. Just because 3, 2, 1 and 1, 2, 3 contain the same set of numbers, it's still the same set of numbers, just in a different order. The order matters, and so we consider them to be different. And that allows for us to have 6 different permutations or 6 different orderings. And so that the order matters here. And that is in contrast to combinations. And so I'm going to move this down a little bit. Combinations. In combinations, the order does not matter. And what I mean by that is, if I wanted to create a combination of numbers from our original set S, right? We had set S right here, and it had 1, 2, and 3. And we were able to create 6 different permutations of size 3 of these 3 items, valid permutations. But with a combination, the order doesn't matter. And what that means is that having 1, 2, 3, a set of 1, 2, 3, this is going to be the same thing as having 3, 2, 1. Okay, all we care about is that this set contains the same items as this set. And because that is a reality, that the order doesn't matter, does it matter? It looks like pi, but it's double T. It doesn't matter. This means that this right here is the only valid combination where k is equal to 3. Right? If someone said, hey, give me a combination that is of size 3, give me all valid combinations of size 3 out of this set, that's 3 items, you would say, well, it's exactly the set itself because the order doesn't matter. We care, as long as the 2 sets have the same items, they are considered the same in terms of combinations. And so with permutations, we're able to create 6 different permutations, valid permutations, because the order does matter, and we consider them to be distinct if they have different orders. But with combinations, there's only 1 out of this set. And there's a formula to calculate this, and you'll commonly see things represented like such. N choose k, where n is the number of items in the set, which in this case is going to be 3, and k is the size of the subset that we want to consider when we're creating combinations. And so in our first example, we considered 3, but let's imagine someone said, give me all possible combinations of subsets of size 2. Well, the formula for this is going to be n factorial divided by k factorial times n minus k factorial. And in our case, since we have 3 choose 2, you can read this as n choose k, by the way, or 3 choose 2 in our case. This is going to be, I don't have to write this anymore. Forget this. It's going to be 3 factorial divided by 2 factorial divided by 3 minus 2 factorial. And 3 factorial, that's going to be 2 factorial, and then 1 factorial. And one of the cool things about factorials is that, this top is this, and the bottom is equal to this. If I have a 2 times 1 down here and a 2 times 1 down here, they cancel each other out. And what I'm left with is 3 over 1, which is equal to 3, which is, it makes sense because all different possible combinations of size 2, there should be 3 of them. Like for instance, we could have 1, 2. Out of this, we could have 2, 3. We can have 1, 3, right? But we couldn't go ahead and do 3, 2, right? Because these are the same thing. And so these are the 3 possible combinations of size 2 out of this set. And so hopefully that clarifies combinations and permutations for you. Now it is time to move on to some more concepts in probability. Okay, so we talked about combinations and permutations and the rule of product and some elementary or some introductory combinatorics concepts. Let's dive into probability. And so probability, we use probability theory for randomized algorithms. So eventually, if you continue in your algorithmic journey, you will get down into learning about randomized algorithms. And these are algorithms that just on average, run in a certain runtime, but they're random. They have a random component to them. And so this is the main use case for it, and especially improving them and building those algorithms. And so I want to start with an example. Examples are the best way to get through these concepts. And so let's consider an example where I am flipping a fair coin 2 times. And so if I have like a quarter or something like that, I'm gonna flip it once, and it may come up heads, and then I'm gonna flip it one more time, and it may come up heads again, or it may come up tails, such and such. And so when we talk about probability, one of the key things to how to think about probability is that we usually talk about a sample space. And we usually denote it with this little omega sign right here in the corner. And a sample space consists of events. And so here we're flipping a coin 4 times, or flipping a fair coin 2 times, sorry. And so there's only 4 possible events that can occur. This one right here signifies us getting 2 heads in a row. This one right here signifies us getting 2 tails in a row. This one means we get a tail on the first flip, and then a heads on the second. And this one is a heads on the first flip, and this one is a tails on the second. And you can represent this set of events as a set. And you can write it such as this: heads, 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 tails, tails, heads, and then tails, tails. And these are all the possible events that can happen in our experiment of flipping a fair coin 2 times. And so it's now time to talk about some axioms, right? So let's get some axioms out of the way. Write that again. Okay, so one axiom is that the probability, this is how I say that, the probability of an event A, any event, it can be this one, or it can actually be these 2 as an event, right? An event is just one or more things happening in the sample space. The probability of any event A being, or the probability of any event A happening is always going to be strictly greater than or equal to 0. So greater than or equal to 0, and that's for all events in the space. The probability of every event in the space, of like everything happening in here, is going to be equal to 1. And so the sum of all these probabilities is going to be equal to 1. And you're probably used to that. A little more real estate needed. But also the probability of any 2 events, the probability of the union of 2 events is going to be equal to the probability of the first one. I'm going to write it like this, plus the probability of the second one, only if they are non-overlapping or mutually exclusive. And so if this was the case right here, we had these two sets of events, A and B, and they didn't overlap, well then of course it kind of makes sense that the probability of everything happening over here plus the probability of everything happening over here is going to be, you know, the union of these two, right? The union just includes everything, and I know that it's kind of bad, but we don't include that center right there. And so that's what that means. And likewise, you know, you can imagine that the probability of the union of two events that do overlap, okay, is going to be equal to the probability of the first one plus the probability of the second one minus the probability of their intersection, right? So we're definitely using set theory here, but we have our sample space, we have our two events, you know, there's probably one or more elementary events in there, little tiny dots, you know, occurring, and this is A and this is B. And so the probability of all of these things occurring is the, or the union is what is the more formally represented. It's going to be the sum of A plus the sum of B, and then we're going to subtract out this intersection. And why do we do that? Well, if we consider the probability of A first, we're going to consider A, and so we're going to consider everything here. And then when we consider B, we're going to consider everything here, including the intersection. And this whole entire intersection got double counted twice, and so we need to subtract it off to get back to just counting those events once. And that's why we do that. And so back to our example here, if I wanted to calculate the probability, okay, of heads, of this event happening, tails, the probability of all of these, okay, which is like, this is A, this is B, and this is C. This is the union of all of them, right? It's going to be the union of all of them, and it's literally just the sum of all of them, right? It's going to be PR heads, you know, plus PR tails, plus the other one as well, heads, tails. And, you know, that's going to be 3/4. Now, why is it going to be 3/4? Well, there's only 4 events in the space. They are all equally likely because we're flipping a fair coin. And so for that reason, you know, this one is going to be 1/4, this one's going to be 1/4, and this one's going to be 1/4. And they're going to take up an equal amount of space because they're equally likely in the probability space. And so the probability of these happening, heads, tails, and then heads, tails, these right here are going to be 3 out of 4. And yeah, so that's the basics. That's the axioms of it, where I explain some very key concepts. Let's talk about an example. Talk about conditional probability. So conditional probability is pretty important. It comes up a lot. And it's just a good way of thinking about certain outcomes of different processes. So the conditional probability is going to be written as such. It's going to be the probability of A given that B occurs. And you can imagine this happens a lot. Something happens, like B happens. Well, we want to know how the probability of A actually changes now that we know that B occurred. And so this can be written more formally as the probability of A intersect B, okay, divided by the probability of B. And so you can imagine if we have A over here and we have B over here, and we know that we're in B, like we know that B occurred. And so we're over here, right? This is where we live right now. This event occurred. We want to know, now that B has happened, what is the probability that A is going to occur? Well, this right here is the only overlapping space, the intersection. This is the only thing that lives in A and also in B. So it's the only A event that can occur in B. And what we're calculating here is just the proportion of B, right, that is A. And so we're taking like A's portion, its proportion of B, and using that as a conditional probability as, okay, what's the probability that this right here happens given that we're in B? Well, it's just the proportion of that space divided by the space that we've allocated for B in terms of probability space. And so let's talk about an example. Let's go through an example. It's the best way to live. And let's flip a fair coin. Okay, let's flip a fair coin twice, like we did beforehand. And let's just say that you flip a fair coin twice and someone says one of those is tails. So let's imagine like your friend of some sorts has a fair coin, and they have flipped it twice, right? They had 2 trials, they flipped it twice, and they say one of those were tails. You don't know if it was the first one. You don't know if it was the second one. You don't know if both of them are tails, right? So like you don't know which one, whether it's the first or the second slot that was tails. And now they turn to you and they say, okay, what is the probability that the other one is heads? Remember, you don't know which order the tail came in. You don't know if it came in first or second. So they're saying it did happen. This really happened. Well, what's the probability that there's a head as well? And so these 2 events, they can be defined as such. They can be defined as event A. And so this right here is just, A is just going to be the probability that a head even occurred. And there's only a couple ways that that's going to be able to happen. We have head tails. We had tail heads, right? We had head and then head. All of these, a head occurs. Tail tails does not count. So this is like one head. And then B is going to be everything such that a tail occurred. And so that's going to be like tails tails, tails heads, and then heads tails. And we want to find the probability of one tail. We want to find the probability of A given that B has occurred. We know B has occurred. We know that we have one tail. But we want to say, what is the probability that a head has occurred? And so this is going to be, we know this is going to be probability of A intersect B divided by the probability of B. Well, if we draw our sample space again, right, we have head, head over here. We have head, tail right here. We have tail, head right here. And we have tail, tail. And A, so what we're going to first figure out what is A. A is going to be head, tail, tail, head, head, head. So this is going to be A. All right, this is A. And I'm going to switch colors. And this right here is going to be B. So tail, 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 head, head, tail. This right here, I'm going outside the boundary, but you get the picture, is going to be B. And the probability that A happened given that we're in B, so we know we're in B. We live here. This happened. We know a tail has occurred. What is the probability that A has also occurred? Well, the only portion of A that actually exists in B is this portion right here where a head actually occurred. And so we know that the intersection of A and B contains 2 events, right? And so the intersection of A and B contains 2 events out of all 4 that occurred. And let me give myself some more real estate. And we know that the probability of B even occurring is, well, B has 3 events, and so that's going to be 3 over 4. And this is just another way to write 1/2. And so I'm going to rearrange this. It's going to be 1/2 times 4 over 3. That's going to be 4 over 6, which is equal to 2/3. And so the probability that if you had flipped a fair coin and one of it was heads, we don't know which slot it was in, first or second, what is the probability that the other one is heads? Is going to be 2/3. And that is how we can use conditional probability to answer that question. And so that concludes our short lesson on the intro to probability. We're going to take a deeper dive and talk about discrete random variables and why they matter. And so this video is on discrete random variables, and I kind of want to first start off by not defining a discrete random variable, but talking about what a probability distribution is and what is a discrete probability distribution. And so you've commonly seen probability distributions. You have seen probability distributions, but usually I think the most common ones are continuous. Like we're used to the bell curve. We've pretty much everyone has heard about the bell curve, and it's literally just a continuous distribution like such. And you know, if you talk about a standard normal distribution, it would be centered at 0, and so it has some standard deviation, etc., and it goes out to negative infinity and infinity, and so that's on the real line. And each point, or each little area under this distribution right here, represents like some probability of things happening in this range. So this could be like -1 to -0.5, and this area would be the probability of anything happening in this range. But this is a continuous distribution, and a continuous distribution just means that, you know, the number of numbers that can be on this line is infinite, because real numbers are numbers like 0.23, 0.231, 0.2312, and then 0.23123 ... And so it can actually just go on forever. You're never going to get to a point where you can't find another real number in between two sets of numbers. And because of that, it's infinite and it's continuous. But in algorithms, we deal with discrete probability distributions. And in computer science in general, we deal with discrete probability distributions. I apologize for my handwriting. But what's a common example, one that I like the most, is we have, let's imagine we have an example where we have a fair die, not a fair coin, but a fair die. You're trying to figure out what's the probability that if I roll this die, I get a 1 or a 3 or a 6, you know? Well, you can represent the probability distribution for this as such. We have 1, 2, 3, 4, 5, and then 6. And then each one of these, because the die, each one of these are equally likely, and because they are equally likely, they all have the same probability. And since there's 6 possible events, you can get between a 1 and a 6 on a die. That means that each one of these has a probability of 1 over 6. And because these numbers are countable, there is no such thing as 1.5. There is no such thing as a 2.25 or a 3.1 or anything like that. They're countable. There is a fixed number of outcomes that can happen. It is a discrete probability distribution. And that is what a discrete probability distribution is. And so let's continue this by talking about discrete random variables. What is a discrete random variable? Let's say RV. Well, this is a discrete random variable. We can denote a discrete random variable being x. A discrete random variable x is a function. It is actually a function. And what it does is it's going to be a function that can act on a sample space. Where if you apply, or if I wanted to say what's the probability that x is equal to some event little x, that's just going to be all events in our sample space S, such that x passing that event into x is going to give me little x. And so a discrete random variable is a function, and to distinguish it from a discrete probability distribution is to say that a discrete random variable produces a probability distribution. So what does that even mean? Let's do an example. So here's our example. Let's imagine that I rolled a die 2 times. I rolled it once, figured out what it was, rolled it twice, and then figured out what it was after that. And I'm going to let x be our discrete random variable, and x is going to be the sum of the 2 die rolls. So whatever I get on the first one plus whatever I get on the second one. And you can see this is a function. And so what I'm trying to figure out is, okay, what is my sample space? And I'm going to draw the sample space a little bit differently, just because it's going to make a lot more sense. It's not just going to be points and some, omega sign. But maybe I'll include omega so we have some, some sense of familiarity. And I'm going to draw a table. All right, so I fast forwarded a little bit, and let's imagine this is our sample space. I didn't want you to see me just drawing lines. It's only a small example. 5 and 6. And so you can read this as such. So this right here is going to be the first roll, and this right here is going to be the second roll. So this cell right here, this is going to be the probability of you rolling a 4 on the first roll and a 4 on the second roll. This right here is going to be the probability of you rolling a 6 on the first roll and a 5 on the second roll. And what we want to know is, I want to know this. I want to know what is the probability that x, our random variable, is equal to 5. What is that? Well, let's think about it. So I'm going to take x and I'm going to pass in all these different little tiny events that can occur. This one, this one, this one, this one, this one, and this one. And I'm going to see which one of these actually produces a 5, where I sum them up, the two numbers up, the first and second roll, and get a 5. Well, if I do 1, 1, and I sum that, if I get a 1 on the first roll and a 1 on the second roll, and I do x of s here, this particular event, I'm going to get 2, and that's not equal to 5. And so let's move on. But I do realize that if I get 1 on the first roll and I get a 4, well, that's going to be equal to 5. 1, 5 is going to give us a 6. And, you know, just to speed things up here, if I get a 2 and a 3, that's going to be 5. If I get a 3 and a 2, that's going to be 5. And if I get a 4 and a 1, that's going to be 5. And so these right here are going to all the events in all of the sample space of all these 36 squares right here. You know, 6 times 6 is 36. These are the only ones such that when I took my random variable x, this function x, and right here, this is the function, and I pass the little s, that event, these little boxes, I pass them into x, I actually got 5. And then what I want to do now is figure out what's the probability of that. What's the probability that I do 2 die rolls now and I get 5? Well, that's going to be the number of different cells that actually produced a 5, which is 4 of them, divided by the total number of cells, the total number of outcomes. And it's 4 over 36, which reduces to 1 over 9, and that is our answer. And so that is an example of how a particular random variable can produce, you can calculate the probability of a random variable. Now, in terms of its probability distribution, this probability distribution would be over, from 2 to 12, right? That's the lowest number you can get is 2, because you can do 1 and 1, and then the highest number you can get is 12, so it's going to be from 2 to 12. And so if you think about it, you have 3, 4, 5, ... all the way to these numbers in between, and each one of these has a probability, where we know that the probability of this one, right, is going to be 1/9. Well, what's the probability of 2 right here? Well, the probability that we get 2 is just going to be this right here. Well, that's not that likely, you know what I'm saying? So that's only 1 over 36, because this one's going to be really small. What's the probability to get a 3? Well, it's going to be 1, 2, or a 2, 1, and that's pretty much it. And so that's going to be 2 over 36, or 1 over 18, but it's going to be a little bit higher, 1 over 18. And so this is going to produce a probability distribution, but the only way I produce the probability distribution is by applying x to all the events in the sample space. And then figuring out what's the probability of it actually happening. And that's how that's going to work. And so that is a little bit of an introduction on discrete random variables and discrete probability distributions. One last thing that I want to teach real quick is that we can calculate the expected value. You can also calculate a variance, but this is probably the most important, is that the expected value is written like this. The expected value of a random variable, it's just going to be the sum over all possible events x of x times the probability that this random variable is actually equal to x. And so if we wanted to calculate the expected value of this distribution, it would be this. It would be 2 times 1 over 36, because this is an outcome times its probability, plus 3 times 1 over 18. And then I'd keep on doing that for all of them, and I would sum them up, and that would give me the expected value of x. And so that tells me on 2 different rolls, what is the expected sum of these two rolls, since x is the sum of those 2 different die rolls. And that is the expected value, so that's also very important. So I want to discuss recursion in this video. So what is recursion? And maybe you've heard about this, if you've taken any computer science courses, recursion gets brought up all the time. In a more general sense, if you look up the definition of recursion, it's going to say that it's a problem-solving method. Problem-solving method, where the solution to a problem, like the solution, right, sol, depends on smaller subproblems. And that's a very general statement, but and nonetheless is what you'll get. In this video, I want to discuss more specifically recursive functions. Okay, and recursive functions. So what does this look like? So what we're really used to, we're used to functions that look like this: f of x is equal to x squared. Or, we've used to a function that may look like this, like f of x is equal to 2x plus 2. These are functions that we're used to. We've seen this in grade school. It's something that's common. However, these are what I would deem as regular functions. They're just what we're used to. A recursive function is a little bit different. So let's say I wanted to write the recursive function. Let's just say these are regular. Okay, a recursive function would look like this. Let's write f of x is equal to 1 if our input is less than or equal to 1, and if not, it's equal to f of x, write it like this, f of x over 2 plus x squared if x is greater than 1. And this part right here, recursive functions have what are called a base case. They all have a base case. And then this right here is the recurrence within the function. And what's going to happen is that if I was to call f of 4 right here, well, f of 4, that's going to be greater than 1. This is going to be equal to f of 4 over 2, right, which is 2. So let's just write 2 right there, plus 4 squared, right? And then, well, f of 2, we don't know what that is yet, so we have to call it again. F of 2 is greater than 1, so it's going to call, well, f of 2 over 2 is just 1, plus, 2 squared. And then f of 1, well, at f of 1, x is less than or equal to 1, and so we're just going to return 1. And what's going to happen is that here we stop. And then all these missing values that we had, because we didn't have the solutions to them anymore, they're going to start bouncing back up. So f of 1, we're going to fill it in here. This is going to be 1. And then this f of 2 right here is now equal to 4 plus 1, which is 5. And so it's going to be sent back into here, which is going to be 5. And then 5 plus 4 squared is going to be, 4 squared is 16. So f of 4 right here is going to be equal to 21. And so under this function, right, f of x, f of 4 is equal to 21. And that's a lot different than what we're used to, because if we look at number 1 over here under our regular functions, right, f of 4, we just only had to put it in one time, and we'd get back, x squared is going to be, 4 squared is going to be 16, right? But the thing is with this recursive function is we sent it in, and there was a portion of the function that required us to call the same function on a smaller input. And so hopefully you're piecing together this whole broader concept of a problem-solving method where the solution to a problem, what's our problem is f of 4, depends on the solution to smaller subproblems, f of 2, f of 1. And every recursive function has a base case. It also has a recurrence. And that is the main components of a recursive function. And so when we're analyzing algorithms, one thing that really helps us is being able to take our recursive function that we had and that maybe it explains, it defines some sort of algorithm that we currently are using. Take that recursive function that we have and find a regular one that bounds it, a regular one that bounds it up to some constant, proportional to some constant. So what do I mean by this? Let's start with this example here. Okay, and so this is a recursive function, and it's going to be f of x is going to be equal to 1. This is our base case. If, let me write this out a little bit further, if the input is less than or equal to 1, else it's going to be equal to f of x over 2 plus f of x over 2 plus just x if x is greater than 1. And so if I asked you, what would be f of 16, right? You would have to go through all the steps and plug it in and follow the recursion down each level, and it would be very tedious. And we're dealing with algorithms, and so we really just want to say, hey, is there some way I can analyze this function real quick and just see that for any input I can use this regular function, something that we're used to, that's like the log or x squared plus x, something else, to evaluate it. So I don't have to keep doing the recursive steps. And so that's what we're about to do. So let's think about this. And so we can do this using a recursion tree. There's actually several different ways to analyze recursive functions, and they're all very suitable when you're analyzing more complicated recursive functions than the one we have. But this is a good way because I think it helps you visualize it as well, and visualizing is always good in math, and it also you understand recursion very well when you think about it this way. So let's do a recursion tree on our function. And so I'm going to start off with x at the top because that's our initial input. And what happens when I pass x into here? Well, we know that eventually x is going to be returned, but first we have to solve these two subproblems. And so we know that after this, f of x over 2 is going to be called here, and then we're also going to do f of x over 2. And then we know that here we're going to have x over 2 called and x over 2, or x over 2 returned, but we first have to solve the subproblems. And so this is going to be f of x over 4 and f of x over 4, and this is going to be f of x over 4. Again, f of x over 4. And then so on and so on. You can imagine, and I'm going to go down a little bit. And you can imagine until eventually, we're all going to get down to where we hit our base cases and we're just going to return 1. Because the size of this input is just going to be so tiny that it's going to be less than 1. And then eventually it's all going to pop back up and pop back up and pop back up until eventually we can evaluate our function. But here's the thing. What if I could find just a regular function, something that I can just plug in a number and get a response without having to go through all these recursive steps? One way to analyze this function right here, its value, is let's first look at what would be the number of levels of this tree. Number of levels of this tree for any given input x. And if we think about this, what's really happening is that at each step, the size of the problem is getting split in 2. And the size of the problem is getting split in 2. And the number of times that I'm going to be able to split a problem in size in half until eventually I get less than or equal to 1, that is the same thing. You may not know this, but that is the same thing as taking the log base 2 of my input. And so if I had the log base 2 of 8, that means I could split 8 3 times before eventually my value is less than or equal to 1. Because, you can take 8. All right, let's split it once. That's going to be 4. Split it again. That's going to be 2. Now we're at the second time, right? Split it again. It's going to be down to 1. And then we have 1. We split it once. We split it twice. 3 times. Got it. And that's roughly as long as your number is a direct power of 2, exact power of 2, this is what's going to be the answer. And we're only going to be dealing with exact powers of 2 in this lesson, and so that's really all that matters here. And so I know that for any given input, I'm going to hit the number of levels is going to be equal to this, right? And so I'm going to write here, the number of levels is going to be the log base 2 of x. And next thing you do is you look up, okay, you think about it and you go, all right, so what is the total cost per level? Per level. And what this means is like, okay, let's look at this level. All right, at this level right here, at x, right? How much actually gets returned right here is just x. Right, because the rest of this gets solved down here. And so what's going to happen is the total cost down here is x. And then if you look at this level right here, for any of these two, what do we call nodes, like this node right here, this input, what's going to be returned here is just going to be x over 2, because we passed x over 2 into here, and that's going to be added over here. And then the x over 4s are going to be solved at smaller subproblems. And so right here we have x over 2 that's returned here, and then x over 2 that's returned here. And so for this entire level, we have x over 2 plus x over 2 returned. And x over 2 plus x over 2 is just x. And we can keep that same logic and say this is going to be x over 4, and then the rest is going to be solved with smaller subproblems, x over 4, x over 4, x over 4. And if we add up x over 4 times, then we have x returned here. And so the cost per level is x. And so now that we have the cost per level and we have the number of levels, we can now actually figure out what our total is. And our total is just going to be our cost per level times our number of levels, which is just going to be x log 2 of x. And I know this is, let me go ahead and delete this one x here. Thank you. And this is our regular function. And so the thing is that this function right here will not always be exactly x log 2x. The thing is that it could very well be a little bit less, it could very well be a little bit more, depending upon the size of x. But at the very least, what we have found is something that says, that looks good right there. That's enough real estate. We can say that our function up top, which is this f of x equal to, let me write it again, if x less than or equal to 1, or f of this right here is always going to be less than or equal to c, some constant, times x log base 2 of x. And I promise you that this function right here, you can find a constant c, like 1.2, 1.4, or 2 or 3, something like that, such that if you plug in any number, like if you did f of, let me get a little more real estate, such that if you plugged in f of, I don't know, 100 or f of like 16, you're going to get a number here, right? This is going to return a number that is going to be less than or equal to whatever you got here. And so you really could just use whatever you decided on your constant, you could just use this function, and it's going to be, greater than or equal to this right here. And in algorithms, that's really all that matters. It would actually be c times 16 log 2 of 16. And I challenge you to play with the constants. See if you can find a constant, right, that upper bounds this recursive function. And now you're just dealing with this. You say, I'm not going to look at this anymore because that's a lot, and I'm just going to turn my attention to this. Maybe you came away with 2x log 2x, and I'm just going to look at this one right here. Much easier to think about than that recursive function. And if we can say that this recursive function right here is bounded above by x log 2x, then that's to say that what that is how we can write that is that we can write it as this. We can write it as, let me clear up my space a little bit. Well, we're saying that this recursive function is less than or equal to c times some log of x. This is the same thing as saying that f of x right here, okay, is big O of x log base 2 of x. And that's what big O means. If you've seen big O notation, it just means that, you know, there exists, and we'll go into this further later on, but there exists some input, some size input, like this is x equal to 0, maybe this is x equal to, I don't know, 10. That from then on out, if we have our regular function f of x, right, maybe it looks like this, and then this one that we have over here, I'm going to change colors, that after this point right here, this new function c times x log 2x is always going to be greater than our other function. And in programming, that's a very powerful statement. And so hopefully you've gained some intuition about how we can analyze an algorithm that, or analyze a recursive function that could represent an algorithm, and maybe you got a little bit of an introduction to big O notation and really a graph of like what that means.